Okay, good morning, students. Today we will begin with some particular techniques used for elemental analysis. So, last class we have seen the different modalities involved in conducting elemental analysis. Different aspects of elemental analysis we have discussed. So, this time we will specifically uh, go through each and every technique, okay, with different aspects and how they are used, the working principles, and the experimental setups like that. Okay, so we will today we will start with the first technique, that is called proton-induced X-ray emission spectroscopy, or it is abbreviated as Pixe. So the title itself show you certain important aspects of this particular spectroscopy or elemental spectroscopy. Okay, so there is proton involved, or it may be sometime positively charged ions. Okay, so let us see one by one. This is a typical experimental setup or laboratory setup used for Pixe. Okay, so we need accelerators, the charge particle obtained drawn from the accelerators. Particle accelerators are used. They are exposed, or they are bombarded on certain targets. Targets will be of the material of our interest, analytical interest, that may contain certain unknown elements whose responses are measured, are observed, are detected and measured. Okay, so it involves a lot of steps, procedures, and techniques. So let us see one by one. So first, it was actually started. The procedure was started in 1917. The first person was Sven Johansson of Lund University in Sweden. She is one of the Swedish university. So he was the pioneer in proton-induced X-ray emission spectroscopy. Initial procedures he began with, and this is a multi-elemental technique. That means you can detect so many elements present in the sample at a time. Okay, and it is comparatively of high sensitivity. That means you can detect it even if the elements are present in milligrams or micrograms. Yeah, that means it offers parts per million or parts per billion sensitivity. It is added advantage, and it is primarily a non-destructive method. So that means what? Sample will not be destroyed. Sample can be retained or archived for later uses. Okay, so there are certain other techniques which may not be so non-destructive. So sample may get destroyed. Its properties may get destroyed. Okay, so come to the basic principle. So this is the basic principle of proton-induced X-ray emission spectroscopy. So it consists of, as I told you, it make use of a beam, proton beam, a high energy proton beam drawn from an accelerator, maybe from a LINAC, maybe from a cyclotron, or from any other accelerating source. Okay, and what happens actually when the protons collide on a particular atom? So consider this an atom with a nucleus at the center. So we have a number of electrons in the different shells. Okay, so the protons, the moment the protons hit the atom, what happens is the electrons from the innermost shells are ejected. So those shells which are closer to a nucleus, okay, maybe K shell, L shell. So K, L, M, N, it goes like that, you know. So what happens when electron is ejected from an inner shells? A vacancy is created. The vacancy is created in the innermost shell. Maybe in the K shell. K shell itself contains so many subshells. Keep in mind. Similarly, L shell may also contain number of subshells. So electrons from those subshells are getting ejected out of the atom. So obviously vacancy is created, and that vacancy is unstable. Unstable in the sense that electrons from higher shells okay, higher occupying shells may make a transition to these lower shells. Okay, so what happens when these transitions are made from higher shell to lower shells? Energy has to be liberated. Energy has to be liberated because when electron make transition from higher shell to lower shell, energy must be emitted. So that may be in the form of photons. Specifically, it may be X-ray photons. X-ray photons. Okay. So X-ray photons. So what happens? Those emitted X-rays will be characteristic X-rays. That means those X-ray will be unique for that particular element. Suppose you are using magnesium as a target, or copper as a target, or boron as a target. Anyway, it may be any atom. So what happens? The emitted X-ray will be unique for that particular atom. Suppose a particular X-ray is emitted by say iron, then that X-ray will be only emitted by iron. Okay, no other element will emit that particular X-ray energy. Okay, so that's the meaning. And the energy of the emitted X-rays indicate the nature of the elements present in the sample. So that is the uniqueness. Okay, energy, that X-ray energy can only emit by that particular element. No other element other than iron, for example, can emit that particular energy. So you can say this is a signature or a fingerprint of that particular atom. Okay, so that by that way we can detect the presence of a particular atom in a sample. And of course, intensity of the X-ray, that's a measure of the quantity of the element. More the amount of that particular element in sample, higher will be the intensity of the X-ray. Okay, so that's schematically the phenomena is shown here. You have a proton or a positively charged particle impinging on the electrons in the subshells or in the shells, in the remote shells, by which electron is ejected out, proton also getting scattered out, and a vacancy is created. Into the vacancy, electron from the outermost shells come and occupy. Okay, this is a brief principle of the work. Okay, the mechanism. So this is visually displayed here. You have the X-ray emitting now. Okay, so the X-ray emitting may contains you have the signal X-rays. This is the actual signal which you want, and along with the signal there may be noise also. So noise is shown with the patch. This reddish patch is the noise, and the sharp spikes are the signals. So this noise is a big problem in many of the such experimental procedures. So noise can be reduced by or minimized, or can be minus, subtracted from the signal, but using certain logical, okay, binary logics, digital logics can be used. You can subtract, but still it is there. Okay, it's a problem. Noise is a problem. So this noise is actually also called a Bremsstrahlung noise or Bremsstrahlung signal. We will come across those Bremsstrahlung aspects very shortly. So schematically, what kind of transitions are taking place in a Pixe phenomenon is shown here. We have number of levels. K level is there, L level, or shells are there, and you can subdivide the shells into subshells. We have, for as far as L shell is concerned, we have L1, L2, L3, and for M shell you have 5 subshells, and the transitions are possible from all these subshells into lower shells, lower levels, and which results in X-ray emission. So for example, all the transition to the K level is called K series X-ray or K X-rays, and all the transition to the L levels, we classify them as L level X-rays. Okay, similarly you have M level X-rays like. Okay, so they are all fingerprint, in the sense that they are unique. Their energy may be unique, so that uniqueness gives us the idea about the presence of a particular element in the sample. That is a key aspect of Pixe. And this is a typical Pixe arrangement. You can see a long steel cylinder, and with an evacuated tube here, it's a drift tube, and you have the collimator here. What is the role of the collimator? Collimator simply focuses the proton beam or ion beam into a narrow one, and it is allowed to bombard or collide on the target sample placed here. This is a target holder, and it is maintained at around 45 degree. Okay, and it's a vacuum tube actually. And after impinging on the sample, the proton penetrates to this backup. It is usually made up of some polymeric material, thin polymeric material. So protons can usually penetrate to this polymeric material and fall on the cup. This cup is actually called a Faraday cup, and a Faraday cup will give the that pulses, electrical pulse to a current integrator, and the current integrator will record the total amount of charge, protons incident on this cup, because this charge value is very important in calculating the amount of substance or amount of element particularly. And the emerging X-ray from the sample you can collect using a silicon lithium detector, CD detector, or semiconductor detector. And using the detector, energy of the particular X-ray can be measured. You can measure energy as well as the intensity of the X-ray. Both are valuable. Energy will tell you about the type of element present in the sample here. And the energy, of course, the intensity will tell you the amount of that particular element. That may contain a number of elements, that may contain a single element. If there are number of elements, the multi elements, you get the different signals of different intensity or different energy. If it is of a single element sample, you will get a monochromatic X-ray. So that depends on the sample composition. Okay. So once the signal is received and analyzed, you get all this data. Okay. The type of sample as well as the amount of sample. So both the quantitative and qualitative measurements are carried out. So this is a typical Pixe, as I already remarked, and you can see the spikes over it. These are unique for different elements. Unique, say for here, for example, here aluminum, sulfur, carbon, calcium, nickel, like that, so on. So for a particular sample, maybe like that, you can get the energy value from the horizontal axis and the intensity value from the vertical axis. Okay, so this is called a characteristic peak. So characteristic spectrum, and this is continuous spectra. Okay, both are there. And this continuous spectra, as I told you, happens due to the Bremsstrahlung phenomena. Okay, Bremsstrahlung simply means breaking radiation. That's a real meaning of Bremsstrahlung. Breaking means something getting slowed down. Here protons are getting slowed down, so resulting in the emission of certain radiation, that is called Bremsstrahlung. So there are various reasons for the emission of Bremsstrahlung actually. There are few factors which can contribute to Bremsstrahlung are electrons ejected from the elements as a result of the Coulomb interaction of the incident projectiles. So it means what? You have the protons, their MeV energy protons are incidentally on the sample. So what may happen? Many electrons are getting ejected. So that also provides signal. High energy electrons can also fall on the silicon detector. That may give you a signal. So electrons can contribute, ejected electrons. There's a flux of electrons that can contribute to signal. That is not signal actually, it's noise. Because signal, you know, that is the X-ray alone. And secondly, you have the energy radiated by the incident protons. Protons may get rebounded, and protons are also getting decelerated because they are falling, striking on a target. So their energy is getting converted into some other retarding energy. So this is also called synchrotron. It is similar to synchrotron energy, proton synchrotron. So that is also sort of deceleration or acceleration. So here also protons are getting decelerated, so their energy is converted into, their kinetic energy is converted into some electromagnetic photons. So that also contribute in the form of Bremsstrahlung. And you have the third factor, gamma ray photons emitted from the wall of the detector. Because we have the steel wall, we have a container. Some of the protons may also hit those walls, inner walls, and that may lead to the generation of gamma rays. That also, so these three factors are contributing to the noise, not to the signal. Okay, so summing up these three factors, we count this as the Bremsstrahlung signal. Here the red patch is a Bremsstrahlung signal. Its contribution come from all the three factors. Here, as far as this spectrum is concerned, here this blue patch is contributed by the Bremsstrahlung, and the inner mechanisms are these three. Okay. And now come to the qualitative part we have seen, and the quantitative part is like this. You can take any peak, okay, any unique spike by subtracting the Bremsstrahlung noise. Okay, by you subtract down the Bremsstrahlung noise, the remaining part is the unique characteristic. So I will get the what is the information you can draw from this peak. You can compute, you can estimate the area of this peak. Okay, by some numerical logics, computer logic, you can measure the area of this peak. That area is a measure of the amount of that particular element in the sample. The net area under each peak is proportional to the number of characteristic X-ray emitted by the particle. Okay, so area corresponds to the amount. So that's a very easy and very user-friendly method to measure the sample concentration. Okay, sample concentration will be proportional to the area. So by this way you can measure, you get the two information. One is the detail of the sample, what type of sample is present, what type of element is present. Secondly, how much a particular element is present. And this is a numerical equation used to get the number of unknown elements, nx. So that depends on different factors, like this is the number of protons increasing on the sample, and this is the mass of the particular element. What is the mass of that particular analyte? Analyte means the element of interest, because the sample may contain so many elements. Maybe suppose you are taking suppose coal. In a coal there may contain various other elements like sulfur, magnesium, okay, boron, germanium, like that. That is what is here, not the carbon anyway, because carbon is the matrix element, and Na is nothing but the Avogadro number, and A is the area of the sample, and sigma x is actually called a X-ray scattering cross section, and T is some correction factor of the experiment setup, or attenuation factor, like that you can call, and eta is the efficiency of that particular device. Okay, you cannot expect a 100% detection efficiency for any sample. What does it mean actually? It means that suppose 100 X-ray photons are falling on the detector. Perhaps the detector cannot detect all the 100, maybe detecting 90, 95, like that. So that factor is always there. Okay, always the detector cannot detect the entire photons. So that is why we include a term called detector efficiency. So by knowing all these parameters, you can compute nx. You can compute it small, because nx is a value that you get from your spectrum. Okay, nx, the area will give you the n value nx. So by knowing nx, np, and all the remaining factors, small m you can calculate. That's the mass of the element under consideration. Okay, so this way the unknown sample's mass or unknown element's mass in the given sample can be calculated. So this is a typical common methodology used in a Pixe procedure. Okay. Some other details are also given here. How you get the protons? You get the protons usually from a Van de Graaff or from a electron. So in India there are various universities which operates Pixe. Okay. So this is how the protons are entering into the chamber. The actual setup is shown in this photograph. And you have a nickel diffuser with a set of collimators. So here there will be diffuser. The purpose of diffuser is to make the cross-sectional density or cross-sectional profile of the electron beam uniform, because the incident or incoming proton beam will have a non-homogeneous profile. So profile should be homogeneous, then only the measurement will be correct. So that is made by fixing here some nickel film or thin foil. So once the proton enter through the foil, the proton beam get homogenized, so that that particular beam can be used for irradiation purposes. Okay, and you have a detector. This is called a X-ray detector, silicon crystal doped with lithium. That is the particular detector used here. And you have a data acquisition system. Basically, it contains some software and electronic gadgets with a computer system suitable with installed with the suitable software required for a Pixe. And you have a Faraday couple for beam charge measurement. Here, this is a Faraday couple by which we measure the total amount of protons incident or total amount of protons passed through the sample. And you have a target holder. This is a target holder, maybe a multi-element target or a single element target, because once a Pixe start operated, in order to make it profitable, okay, cost-wise, financially viable, we will make use target ladder holder, so that you can insert one by one. Okay, in a single shot, you can analyze number of samples together. So that is why we prefer multi-targeted, and the entire setup has to be maintained at a very ultra low vacuum condition, usually achieved with a turbomolecular pump or with a diffusion pump along with the rotary pump. Okay, so some special remarks about the detector used. As I told you, we use a silicon crystal. Okay, what is actually happening here is you have a silicon crystal which is suitably doped with lithium or germanium, and once the X-ray photon incident on this crystal, what is happening is in the inside of the crystal, electron hole pairs are created. And since suitable appropriate voltage potentials are applied across the crystal, the positive and negative, these oppositely charged electron and hole pairs will go to respective electrodes and get discharged. As a result, there will be current in the output. Okay, this is called ionization current or electron hole pair current. So that current is a pulse, in the form of a pulse, not a steady current. So that pulse can be properly shaped, and its pulse height, pulse width, everything can be measured. That pulse height is what we are measuring in spectrum. Okay, so this is a cryogenic setup used to hold this silly detector. Okay, because you know silly detector has to be maintained at very cryogenic temperatures, maybe -70 or -100 degrees Celsius. So you need a cryostat. Okay, so inside the cryostat, you can see the top. Within the cryostat, this crystal is maintained, so that so as to avoid the production of generation of minority carriers, thermally induced minority carriers. So that is the purpose of using this cryostat. Okay, so always the detector is accompanied with a cryostat in order to avoid noise. Okay, so thermally induced charge carriers is a noise. So noise can be minimized using this setup. And by converting the resulting charge into a voltage pulse, whose amplitude is proportional to the X-ray energy, a sequence of detectors can be transformed into a spectrum of counts versus energy. These are all the things we usually do in a GM counter or in a simulation counter in your MSc practicals. So spectrum can be obtained. So this is typical spectrum. This is the energy versus the intensity. Okay, each peak in the spectrum corresponds to different elements. So silly detector converts incoming X-ray into electron hole pairs at a rate of 1 pair for each 3.8 MeV of electron. Suppose your incident photon is having a 38 MeV of energy, So it can produce a 10 a set of electron hole pairs. Okay. So accordingly, the peak height will increase because 10 there are 10 electron hole pairs means there will be proportionate amount of current in the output. So current leads to pulse heights. Understand? The crystal is thick enough to capture virtually 100% of the X-ray. So that silicon crystal which we have kept in the as a detector, they are thick enough to absorb all the X-ray incident on the crystal. Okay, so some remarks about the target details are also good enough. We use very thin targets because proton has to pass through it. Depending on the sample, proton should pass through it and hit that Faraday cup. Only then we can measure the proton, proton intensity. So sample preparation is a very delicate, very sensitive process, and after the sample has to be backed up with material like capton, carbon, formol. They are all made up of certain polymeric material, very soft material, so that the proton can be easily passed. And if we are using thick target, correction has to be made. And we have thin sample Pixe and thick sample Pixe. They are experimentally different, procedure-wise different. And in many cases, calibration constant we determine with samples, with standard samples. The related equations we discussed in the previous module. Internal standard, this is also a procedure. Internal standard can also be added to make a relative measurement, and we have the corresponding relative, absolute, and comparative equations. Okay, there are various applications for Pixe. We have already elaborated in the outset. Water samples, because pollution is very major problem in the current world. So industrial pollution effects can be studied. Trace elemental analysis can be done. Water quality in different places can be compared, and aerosol sample for atmospheric pollution. Okay, from metropolitan cities wherever they are heavily polluted, air samples are collected with the air collectors, sample collectors, and sample is subjected to Pixe analysis. Okay, and the forensic samples are also important for identification of crime-related samples. Fragments of bullets, gunpowder, antimony, barium, copper. These are all major content of gunpowder, or blood stains, and even hair samples. Okay. Human hair samples can be made use. You may be knowing some of the major crimes around the world was means probed using the Pixe methods. Okay. Uh, so Pixe has played a great big role in exploring, in unearthing many of the forensic or many of the crimes. Okay, so biological samples, medical samples, because the presence of many elements, even in trace levels, they are very crucial for human body. Such elements are present in human body. Some are harmful, some are useful. Okay, so such things can be identified. And geological samples, measurement of thorium and uranium levels in ore samples. And meteoritic and lunar samples are also important. In space exploration also, Pixe is used. And semiconductor industry for measuring impurity levels of certain elements. How crucial the presence of certain dopants in semiconductors. That determine that is crucial in deciding their properties. So these are also important, and archaeological samples are also important. An example is shown here. One sample excavated from China and stored in kept in Harvard University, and they found that ancient civilizations they used silver amalgam. It's a mercury compound. They found that even in ancient civilizations, people used the silver amalgam to coat gold on certain other copper plates. Gold coating was done using silver amalgam. It's a great exploration. Uh, so students usually customarily use Pixe for identifying many elements present in specimens of archaeological importance. Okay. So these are all typical glimpses of Pixe procedure done in different labs across the world. Okay, and with all the advantages, Pixe has some limitations. Uh, its application is limited with atomic number greater than 40 because of heavy attenuation of X-ray from lighter elements, and extreme care has to be taken in the target preparation. Should be thin, delicate, and proton should be able to pass through it. And heating due to proton bombardment may lead to evaporation of volatile impurities like selenium. So we cannot identify selenium using a Pixe. So now come to the assignment part. You have a very simple assignment here now. So here is the question. What is Bremsstrahlung signals? And what are its effects on elemental analysis process? So you can write a brief note about it as in a single A4 sheet is enough. Don't don't elaborate too much. Confine your reply in a A4 single A4 sheet. You search out. You can take points from both from this module as well as from any other sources. Okay, write a compact reply on this question and submit in due time. Okay, so hope the ideas are clear, and if any ideas are not clear, you can communicate. All are welcome. Okay, so with these comments, let us conclude today's module. Thank you.